Good days to Dr. Dayang. We are Subgroup 1 from STK2073 Scientific Communication and Research Ethics. Today we are going to present our final proposal. First of all, the title of our proposal is Biochar from Sludge and its Potential Application in Removal of Arsenic in Water Treatment. Before proposal presentation, I would like to introduce myself, and my group members. My name is Karen Chi with metric number at 4209. The other two group members are Simon Isi with metric number at 6995 and Bong Yu Cheng with metric number at 2471.
This research aims to provide sustainable solutions for sludge disposal and water remediation, contributing to environmental sustainability and public health improvement.
Going forward, I would like to introduce the contents of our proposal. It consists of introduction, problem statement, objective, literature review, methodology, expected outcome, work plan, and also references.
I'm Bong Chen, and I'm going to introduce about our research project. Malaysia currently produces 3 million metric tons of sewage sludge annually, and the expected production rate is 10 million per cubic meters per year by 2035. We use approximately 3,030 million of US dollar to manage sewage sludge annually, but the current disposal method is only landfilling. This will cause environmental problems. On the other hand, arsenic pollution also reported in several Malaysia rivers. Arsenic will pose risk to public health, so there is an urgent need for effective arsenic remediation technique. By understanding sludge production issue and arsenic contamination in aquatic environment in Malaysia, we aim to produce biochar from sludge, which has a potential to treat arsenic pollution. Our study aims to produce a proper sludge management strategy to transform sludge into biochar to treat water pollution. The research question is how can we produce biochar from sludge at optimal temperature and provide insights to its physiochemical properties and evaluate its efficiency to arsenic removal. The objectives of this study are to synthesize biochar from sludge through pyrolysis at optimal temperature, rate, and residence time, to determine the characteristic of the biochar produced using CHNS elemental analyzer, Fourier transform, infrared spectroscopy, and scanning electron microscopy to evaluate the biochar efficiency produced in removal of arsenic in water.
My name is Simon Isi with the matrix number 86995. Moving on to literature review, biochar from sludge. Sludge is a byproduct of wastewater treatment and can be transformed into biochar through thermochemical treatment. Even though it requires more energy and complicated process to convert it into biochar, however, it is commonly used as an absorbent and biofilter to treat wastewater. Hence, it is very practical and suitable to be used in soil amendment and water treatment. The physical-chemical properties of biochar greatly affect the structure-application relationships. Biochar contains fewer carbon content compared to other lignocellulosic-derived biochar. It has higher hydrogen-carbon molar ratio when pyrolysis occurs at higher temperatures. Hence, it has high surface area and porosity, which makes it able to trap nutrients and minerals. Biochar has electrochemical properties, high carbon content, contains OH, COH, and phenolic groups, has neutral to alkaline pH, negative charge on its surfaces, high CEC, thermally stable, low nitrogen content, and it includes positively charged metals like calcium, magnesium, iron, and sodium. There are several factors affecting the properties of biochar, which includes the factor of temperature, heating rate, residence time, pressure, and sludge treatment. In our proposal, we focus on the factor of temperature, heating rate, and residence time. In the production of sludge-derived biochar SDB by pyrolysis method, biochar is produced through the pyrolysis of biomass in an oxygen-limited environment. In pyrolysis, long chain of hydrocarbons in biomass decompose into simpler substances, results in solid charcoal formation formed by the condensing of volatile substances into a liquid. SDB can also be pyrolyzed through different reaction conditions, such as heating rate, temperature, residence time, or particle size to produce different characteristics of biochar. Table 1 shows the comparison of slow and fast pyrolysis. In fast pyrolysis, biomass is heated rapidly. On the other hand, slow pyrolysis is heated slowly at a fixed temperature. The slower the heating rate and the longer the residence time, solid biochar with lower use of liquid and gaseous products is formed. Slow pyrolysis and fast pyrolysis are different in terms of their maximum reaction temperature and heating rate. Slow pyrolysis is easier to be utilized to separate the byproducts and recover heat energy. In a nutshell, fast pyrolysis is ideal to obtain more yield of bio-oil, whereas slow pyrolysis is more suitable to produce higher yields of biochar. The mechanism of pyrolysis includes the dewatering of biomass, initial decomposition, high temperature decomposition, very high temperature of decomposition, secondary reactions, polymerization, and at last cooling of products. In the application of sludge-derived biochar in water treatment, biochar is generated from sludge and can absorb hydrophobic and non-polar organic contaminants. It is also flexible in production, and the immobilization of SDB with NZV1 enhances the biochar's ability to remove nitrates and phosphates. Based on Table 2, it shows that the rivers in Malaysia has been heavily contaminated by arsenic. Hence, the application of SDB in the removal of arsenic in water treatment is essential, as biochar prepared from sewage sludge can be used as an adsorbent to eliminate water pollutants. Sewage biochar is also better than commercial activated carbon in removing metals to produce a safer biochar. SDB is also excellent in removal of arsenic from water due to the presence of metal oxides. SDB can be adsorbed to remove impurities in water bodies and other methods through physical adsorption, chemical adsorption, exchange of iron to remove arsenic ions through biochar.
My name is Karen Chi and my metric number is F4209. Going forward, I will be talking about methodology in this research proposal. Firstly is the synthesis of biochar from sludge. Collection and pre-treatment of sludge will first be done. The pre-treatment that we are going to use is anaerobic digestion and also hydrothermal treatment, followed by the production of biochar is produced by slow pyrolysis in a lab-scale muffle furnace. It will be heated at 250 degrees Celsius and then transferred into a muffle furnace to be heated at 500 degrees Celsius and in a residence time of 90 minutes. Followed by the characterization of sludge-derived biochar, there are few aspects will be analyzed in this research, which are biochar yield, elemental analysis, by functional groups of sludge-derived biochar and its morphology. For the biochar yield, it will be analyzed using a formula. Next, elemental analysis will be carrying out using a carbon, hydrogen, nitrogen, and sulfur elemental analyzer with model name of Barrel EVL3, which is an elemental brand, followed by the functional groups of sludge-derived biochar. A Fourier transform infrared spectrophotometer will be used in order to detect the functional groups present in the biochar produced. A thermo-Nicolet IS-10 model is used in analyzing the functional group. Next is its morphology. Scanning electron microscope will be used to analyze the surface of biochar produced at 600 times magnification to obtain the information of its surface texture and porosity. Last but not least is the determination of sludge-derived biochar in arsenic removal efficiency in water. First of all is the preparation of arsenic stock solution with a concentration of 10 mg per liter, followed by the absorption test of biochar to remove arsenic. 50 ml of arsenic solution and 0.1 gram of biochar in the digestion vessel will be well shaken and then filtered by using a nylon membrane filter, followed by the quantitative analysis of arsenic absorbed onto the biochar will be analyzed using coupled plasma atomic emission spectrometry to determine the concentration of arsenic 5 in liquid sample.
Our expected outcome is to identify optimal parameters for maximum yield and quality of sludge-derived biochar to provide a detailed physiochemical properties of biochar, demonstrate biochar efficiency in remediating arsenic-contaminated water, and also establish the potential for co-combusting biochar, addressing arsenic contamination in water bodies, and the last, provide sustainable and valuable use for sewage sludge, contributing to environmental protection and public health. These are all from us. Thank you very much for your attention.